Hello again, this is Mr. Thompson again, and this is part two of processing your motion of a trolley down a ramp data. So hopefully you've done your experiment. Hopefully you've done this experiment here where you've rolled a trolley down a ramp and you've timed how long does it take the trolley to reach certain points on the ramp, and you've put your information into your table like this. And of course you remember the first video I gave you showed you how to create your table. So hopefully you created your table, you did your experiment, and you've got something like this. All right, there's a fair bit to cover, so I'm going to get straight into this, how to process this information. Now, actually, before I get started, here's what I'm going to do. Let's look at what are we after? What are we trying to achieve? So what we're trying to achieve is we're trying to build two graphs. We're trying to build a displacement time graph, and it should look something like this. It should be a sort of a parabolic curve, a parabolic graph, which shows the slope of the graph, that is the velocity, increasing as the object goes down the plane. The second thing we're going to do is we're going to try to create a velocity time graph, and the velocity time graph should be, if everything works out correctly, should be a linear graph like this one, where the velocity increases linearly with time. So they're the two graphs that we're going to try to get from our data. Let's cross our fingers and let's see how we go. All right, so the first thing I'm going to do is, I'm going to just fix up this data here. In fact, I'm going to select the whole table here, and I'm going to fix up those decimal points. So I'm going to use these two buttons here, and here we go. I'm going to change all the decimal points. So all of our decimal points have all our numbers have two decimal places in the whole table, except for the distance. You know what? We could do the distance as well. Let's make them all two decimal places, because we would have measured the distance to two decimal places, so that makes sense. All right, there we go. First thing we're going to do. Second thing is calculate averages. So I'm going to click here on the first cell here, and I want the average of all those numbers. Now this one's trivial. Let's do the formula anyway. So equals average, and then open brackets. Average of what? Average of all of those cells there. Close the brackets. Hit enter. Okay, and we knew that the average of all of those noughts was just going to be naught. Okay, but let's look at some of the more interesting ones down here. Now what I can do, instead of typing that formula in again, I can just grab, select that cell, so select that cell, and then grab that small rectangle, that small little square there at the bottom right corner of the cell. That's my autofill handle, and then I can drag that down, and that uses the exact same formula for each of those cells. So it's calculated the averages, all of my averages for me. It stuffed up my formatting a little bit. That's okay, I'll fix that up in a minute. All right, UOM, uncertainty of the mean. I'm not sure if I will have discussed this in class yet, but let me quickly explain what uncertainty of the mean is. You might have heard of stuff like range or standard deviation, different ways of measuring the spread of the data. So uncertainty of the mean is effectively half the range. It's a measure of how far apart your data has been spread. So let's come down here and do one in the middle. So I'll do this one here first. So the uncertainty of mean is going to be equals the in fact, I'm going to open the brackets there, equals, open brackets, the maximum, open brackets again, the maximum of all of those cells there, close my brackets, minus the minimum of all of those cells again, same cells, those cells, close brackets, and then close brackets again, divide by 2. Okay, so that is our formula for the uncertainty of the mean. The maximum of all of my values minus the minimum of all of those values divided by 2. And again, I'm going to just grab that autofill handle and autofill up and down, autofill all of those numbers there. So what does this tell me? This tells me that this particular set of trials here with the distance of 0.2, I had an uncertainty of the mean of 0.07. That tells me that my data for this particular set of trials here was more spread out than, say, this one here. This one had an uncertainty of the mean of 0.02. That means these numbers here are much closer together than these numbers here. So perhaps I was getting better at doing the experiment by the time we got to the end of the experiment. So that was my set of data that had the biggest spread, and that had my least spread. These two down here. Well, actually, this one had the least spread, didn't it? But that's just saying that at zero distance there was zero time and zero speed. That one's pretty obvious. All right. Let me fix up that. I'm going to fix up that formatting. So I'm just going to select that whole cell there, and I'm going to come up here, and I'm going to go all borders, having a small border, and then a thick outside border again, like that. There we go. That's just fixed up my formatting. Okay, now I've got enough information that I can do my displacement time graph. So let's see. So our distance here really is a displacement, isn't it? It's a displacement down the slope. So I guess what I'm going to do is I want to graph that column there and that column there. And what I really want is I want my times to be on the horizontal axis, and I want my displacements or distances, because it's a straight line, distance and displacement have the same value. I want my displacements on the vertical axis. So how do we do that? Okay, so first we select the displacements or the distances there, and then we hold down Control and we select all the averages. Okay, and then we're going to insert a graph. So insert, we'll come over here, choose an XY scatter plot, like that. And I'm just going to choose the first one. Just choose the first one like that. Okay, and I'm going to bring that one down here. Okay, now straight away I can see this is not really what I wanted, because it's put the average, it's put the times on the y-axis, on the y-axis, on the vertical axis, and it's put the distance on the horizontal axis. So I need to change those. So here's what I'm going to do. I'm going to right click, and I'm going to select data. Actually, let me just show you that again. When I right clicked, I didn't right click on the dots. I didn't right click on the title. I right clicked right up here in a blank area. Yep. So right click and then select data. Now, don't click on this switch row column business here. That doesn't do what you think it's going to do. So don't do that. Here's what we need to do. We need to click on series 1. That's these dots here. And we need to edit the series. Now, our X values, there's our X values. I'm going to select our X values. And our X values at the moment is our distance. To put our distance down the bottom. I want time on our X-axis. So I'm going to delete those, and with my cursor there in X values, I'm going to select the time. That's where I want the time on my X axis. So I'm going to click there, and then my Y values, I'm going to delete all those, and I don't want, and for my Y values, that's where I want my distance or my displacement there. So I'm going to select distance there. Click OK. All right, and now when I go OK, that's the shape of the graph that we expected, sort of a parabolic with the slope increasing as time goes on. Okay, let's tidy this up. Chart title, let's call this, I'm going to double click in here and then Control A and type in a better title. I'm just going to call that a displacement time graph, okay, because that's what it is. Displacement time graph. And now I'm going to click over here, and then I'm going to click on the plus sign, and I want axis titles. So let's see, this axis title down here, if I double click here and Control A to select the whole title, and that's got to be time in seconds. And this axis here, if I double click there, that's going to be displacement in meters. Close my brackets. Okay, so there we go. We've got our displacement time graph done. I'll just expand that a little bit, make it look a bit bigger. Oh, now I'd like to put a trend line in. So I'm going to go plus, and a trend line. Now I'll click on the trend line. It's put a straight line in. Don't really want a straight line. We're expecting a parabolic line. So I'm going to double click on the trend line there, and I'm going to come over here on this side where it says Format Trend Line. A parabolic trend line is actually a polynomial trend line, second order. Okay. In other words, that's just a fancy way of saying it's got x squareds in it, which it would have. We're not going to go into the mathematics of all that. Just take my word for it. It's a polynomial. If you want to talk to me about that more in class, you can do that. All right, and you can see that creates a much nicer line there. Oh, now look at this. Look what it's done. It's put it's actually, because that line has probably dropped just below the x-axis, gone into the negative, it's put a negative number here on my axis. I don't really want that. So I'm going to double click on my axis on those numbers there, and I'm going to come over to here, and I'm going to select this button here, Access Options, and I'm going to set the minimum to 0. There we go, and that's fixed that up for me. Okay, that's a much nicer graph. All right, so that graph's done. Okay, let's talk about the velocity. Now, we didn't have a motion sensor that detects velocity, did we? But we can calculate the velocity using the time and the distance, can't we? So remember our formula for velocity. Velocity is displacement over time. So we've got our again our displacement or distance, because we're traveling in a straight line. The displacement and the distance are the same value, so we're just using distance there. I probably should have labeled that heading displacement, shouldn't I? Then I don't have to explain that all the time. All right. Anyway, so let's use this formula. Equals the distance divided by the time. Which time? Well, we're going to use the average time. So if I click on that, yep. So we've got the distance divided by time. Hit enter. Okay, and there is our average velocity. So that was that. So that velocity, let's think about what that is. That velocity there, 0.7, is the average velocity for the trolley as it rolled from 0 to 20 centimeters. So that means sometimes it was going slower than 0.27 meters per second, and sometimes it was going faster, but on average, that was its velocity. And now again, I'm going to drag down and drag up. Okay, oh, now it's got to divide by 0 there. That makes sense. It's trying to divide by 0, because if my time was 0, then it's trying to do a divide by 0. But we know, don't we, when the trolley was at the top of the ramp, just before we let it go, we know it had a velocity of 0 because we were holding it still. So I'm just going to type 0 in for that top one. I'm just going to type 0 in there for that top one there. Now, the instantaneous velocity. I'll talk about this in class, but let me give you a quick explanation. We said the average velocity, let's work down here. The average velocity here in this row here was the average velocity between when the trolley started at the top and when it got to 20 centimeters. So sometimes it was going faster than 0.27 meters per second, and sometimes it was going slower. If we look at this graph here, we can see that the average velocity is actually halfway between, if we assume that we've got a linear or a constant acceleration, which is a pretty good assumption for this experiment. If we've got a constant acceleration, then we can see that our average velocity for the journey from 0 to 20 centimeters is exactly half of the velocity when the trolley was at 20 centimeters. Or another way of saying that, the instantaneous velocity of the cart when it was at 20 centimeters is twice the average velocity. So we know the average velocity, so we can calculate the instantaneous velocity. So it's simply going to be equals the average velocity times 2. The average velocity times 2. That's our instantaneous velocity. So at 20 centimeters, the trolley was going 0.53 meters per second. Now I'm going to autofill that down and autofill it back up again to the top. And again, I've mucked up my formatting, so I'm just going to fix that. I'll select that whole lot there and put a thick outside border there, like that. All right, so my table's complete. Okay, now I want to create my velocity time graph. So here's how I'm going to do that. Again, I want, this time, I want time, that's this column here, they're my average times, and I want so I want that on my horizontal axis, and if I hold down control, and I select the instantaneous velocity, that's what I want on my vertical axis. So now we're going to go insert, and we're going to click on again an XY scatter plot. We'll click on the first one. Now this time Excel's been much more well behaved. It's put the axes the right way around for us. So that's great. So I'm going to double click here on title, Control A to select the whole title, and I'm going to say this one here is a velocity time graph, like that. And again, I'm going to click up in this right hand corner here and click on plus and add some axis titles. And this title here, if I double click here, Control A, that is velocity in meters per second. Velocity in meters per second. And this down here, this axis here is time in seconds. All right, and that actually looks pretty straight. That's a pretty straight. So let's add a trend line here as well. So what I'm going to do is I'm going to click here again and click on the plus, and I'm going to add a trend line, and it'll by default it'll put a linear trend line in, a straight line. Now I want to know the slope of this trend line, because the slope of this trend line gives me the acceleration of the trolley. So I'm going to double click there on the trend line, and it'll pop up this little options box over on the side. Make sure this icon on the right hand side is selected, and I'm going to come down here. I'm going to click on display equation on chart. And you know what I can also do? I can display the R squared value. I'm going to put both of those in. So the equation there, that tells me, see the Y value, or the coefficient of X there, 0.6121. That's the slope of the graph. So that tells me from my data, the acceleration of the trolley down the ramp was 0.6121 meters per second, according to my data here. What else can we learn from this? The R squared value is a measure of how closely the line fits the points. So if that line went exactly through all the points, then we would have an R squared value of 1. Anything less than 1 means it's not a perfect fit. This is pretty close to 1, 0.9942. So that tells me it's a pretty good correlation. So my acceleration there does look pretty constant. All right, one more thing we're going to do. We're going to calculate that's our experimental acceleration, 0.6121. In fact, let me just type that up here. Experimental acceleration in meters per second. Meters per second. And I'm going to make that right justified like that. And I'm going to calculate. And so that's, I can actually just type that in now. That's that number there, 0.6121. Okay, my theoretical acceleration, theoretical acceleration in meters per second, we can calculate this, and I'm not going to derive this for you, but let me just tell you. So the theoretical acceleration down the ramp is, well, we start with the acceleration of an object in free fall. If I drop an object, it accelerates at g at 9.8 meters per second. But we're not dropping it in free fall, we're letting it roll down the ramp. So the acceleration down the ramp is 9.8 times the height of the ramp. That didn't work, did it? Equals 9.8 times the height of the ramp divided by the length of the ramp. Okay, and that 0.6121, that's what our experiment says acceleration due to gravity was, and this 0.860, whatever that is, 0.860646 meters per second, theoretically that's what our acceleration should have been. Why isn't it the same? Well, that's something for you to discuss. I'm sure you can work that out. Okay, I think that's everything. I hope that was useful.